Hello students, welcome to your second video lesson on trigonometric equations. We're still in section 611, but today we're going to extend our trig equations to not be on a restricted domain like we had yesterday. Okay, yesterday we were just working with a restricted domain or restricted values for x that were on the unit circle. Today we're going to expand that, okay, or extend that. So we're going to start with problem 7, which I believe is somewhere near page 268 or 269 maybe in your textbooks. And number 7 actually shows you a graph. I don't have it on the screen now, but I do want you to turn there and look at that graph. They've graphed for us the sine of x. Okay, they've graphed y equals sine of x. And they've sort of extended out the x values. That's why it looks kind of squished, so that we can see multiple up and downs, up and downs, up and downs like that. And they're asking us sort of about the solutions to this equation here, sine of x equals 0, which basically means on that graph, all the x-intercepts, all the times that the sine of x, the value of the function, is equal to 0. Okay? So as we can see there are a lot of them. There's 1, 2, 3, 4, 5, 6, 7 on that graph right there. And so we are obviously dealing with more solutions than we had in our last video, right? When we had our restricted domain, because this domain looks like maybe from negative 3 pi to positive 3 pi, which is a bigger picture here, okay? So the first question, if we just think back to what we did yesterday, how many solutions are there if we restrict the domain just to the unit circle for this? Like, how many points on this unit circle here have a sine value of 0? Sine value of 0. Well, sine, remember, is the y coordinate of the point. So how many y coordinate on your unit circle are 0? There are 2 of them. 2 solutions, and what are they? What are the x values that have a sine of 0? Well, one of them is right here, and so we have to sort of talk a little bit about this one, because technically on our unit circle, I believe you have that labeled in 2 different ways. It's 0 and it's also 2 pi. Okay, but for our purposes right now, we consider 2 pi to be the start of the next time around the unit circle, so we're going to use x equals 0. Okay, x equals 0. And then the other option is over here, right, over this direction. That point right there is at pi, right? Pi on our unit circle also has 0 as a y value or 0 as a sine value. So 0 and pi are the solutions to this equation if we restrict it just to be on the unit circle from 0 to 2 pi, okay? Now, the question is, how many solutions are there if we don't restrict the domain at all, and we just let the graph keep going forever in both directions, or we keep going around and around and around and around the unit circle forever, okay? Or we go backwards around the unit circle to get negatives forever. How many solutions are there going to be then? Well, it should make sense that there are going to be infinite solutions, right? Because we never stop going around and around, and we're going to go 0 and then pi and then 2 pi, and then we're going to keep going. We're going to hit 3 pi, and then we're going to keep going. We're going to hit 4 pi. We're going to keep going and hit 5 pi and 6 pi and 7 pi, 8 pi, 9 pi, and all of those in the negative going the other way as well. So there are infinitely many solutions if we don't restrict the domain, if we let it keep going forever. The question is, how can we represent all of those solutions? Okay, and in order to get that notation, we just have to think about, if I think about this solution point right here, okay, at 0, at x equals 0, that point right there. From here, how much do I have to add in terms of my angle to get all the way around the circle and back to where I started? How much do I have to add to get all the way around the unit circle one time and right back to where I was before? Well, I have to add 2 pi, because one time around the unit circle in terms of its angle, in terms of radians, remember, is 2 pi. So what I can do is I can take the solutions that I have and I can simply add 2 pi. Okay, so if I add 2 pi to this one, and I add 2 pi to this one, that gets me 2 more answers, right? It would get me 2 pi, because 0 plus 2 pi is 2 pi. And then this one, if I did pi plus 2 more pi, this one would get me 3 pi. Right? It'd get me 3 pi. But remember, we want infinitely many solutions, so just adding 2 pi doesn't get me infinitely many solutions. Now I just have 4, right? Well, okay, I could also subtract 2 pi, right? I could go the other way and minus 2 pi, and I'd end up back at the same spots as well. And I would end up with negative 2 pi for this one. And this one, if I went backwards by 1 whole time, I would end up at negative pi. Okay? So that gets me 2 more answers, but that's still not infinite answers. So adding 2 pi doesn't quite get me all the answers. Subtracting 2 pi in addition to that doesn't quite get me all the answers. But the good news for us is we can continue to go around the circle over and over and over again as many times as we want, right? We could go around the circle 2 times, and that in that case would add 2 pi twice, right? Add 2 pi and go around, add 2 pi again, go around, we've got another answer. We could go around the circle 5 times. Add 2 pi, add 2 pi, add 2 pi, add 2 pi, add 2 pi. We still end up at the same spot and we get another answer. So we can add 2 pi as many times as we want to. So what we do to represent all of our solutions is we add 2 pi times n. Okay, and then we just say n is an integer. Okay, so integer, remember, is a positive or negative number with no decimals. So we just add 2 pi n, and then we say comma n is an integer. N is integer. Okay, and that's sort of an algebraic or mathematical way to represent going around and around the circle as many times as we want, and the n represents how many times we want to go around. Okay, so what I can do then is I can say, okay, one of my solutions is x equals 0 plus 2 pi times n, where n is an integer, because that gets me the first answer, and then every answer after that, going around the circle over and over and over and over again. Okay, and then I can also say, well, x can also equal pi, and I can do exactly the same thing. I can add 2 pi times n, where n is an integer, and that will go around and around and around the circle and hit this point over here, pi, and hit that over and over and over again with different x values or different angle values. Okay, so that is how we represent all the solutions. Now, I will allow you to sort of simplify this down, and instead of writing it out 2 times totally separately, I'm okay if you write them all sort of in the same line. What I mean by that is we can just write this. We can simply write x equals 0, comma pi plus 2 pi n, 2 pi times n, comma n is integer. Okay, that's an okay notation for me. It saves us some time and some pencil lead, as opposed to writing out that plus 2 pi n twice with n as an integer. So this here would be a representation of all the solutions to sine of x equals 0 on an unrestricted domain going both directions forever. Okay. Number 9. 6-9, which is on the next page for you guys, basically wants us to do the same thing, but it wants us to do it with the equation we looked at yesterday. Okay, sine of x is equal to a half. So I've already given you sort of what they gave you. The dots on the unit circle at the right signify the points that reveal the solutions to this equation, right? Sine of x is equal to a half at this point and this point. What are those points in terms of our angles in the unit circle? Well, this one here is pi over 6, and this one here is 5 pi over 6. So those two values of x satisfy this equation, right? But those are only the values that exist on the unit circle, right? How do we represent all the solutions? Again, we plus 2 pi n where n is an integer. So what we can say in terms of solutions to this equation on a totally unrestricted domain, we can say x equals pi over 6 and 5 pi over 6 plus 2 pi n, and then we'll just say where n is an integer. Okay, and this is a representation of all the solutions starting here and going around and around and around and around and around and going over here and going around and around and around and around and around to get all of my solutions. Okay, so we're going to start seeing problems where we're asked to solve these on unrestricted domains. What that means is they just want it to extend forever. And obviously, you know, our sine and cosine graphs keep going up and down, up and down, up and down. So we have infinitely many solutions if we don't restrict our domain. Now, one other thing to be aware of is that sometimes there's actually a more simple way even than adding 2 pi n to represent all of these solutions. Okay, and I just want to throw that out there. I'm never going to mark it wrong if you just add 2 pi n over and over again, but you may at one point see something like this. So I'm going to go back to my unit circle, and I'm going to go back to asking about the sine of x equals 0. Okay, so remember we talked about that being here and here at 0 and pi, right? 0 and pi. And then if I were to keep going around and around the circle and represent or list out more of my solutions here, remember that if I add 2 pi to this one, I get 2 pi. And if I add 2 pi to this one, I get 3 pi. And then if I add 2 more pi here, the next one will be 4 pi, and then this would be 5 pi. And then the next one here would be 6 pi, and the next one over here would be 7 pi. And I want you to notice that I'm really, if I just combine these together, I'm hitting every single number pi, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and on forever, right? So I don't need to add 2 pi. I can actually just add 1 pi, and that will get me another solution, okay? And that's going to happen when we do sort of things with solving maybe tangent equations later, or sine of x equals 0, or cosine equals 0, or sine equals 1. No, just kidding. Sine squared equals 1 would be 1. So anyway, sometimes we see these types of patterns in our answers, and then we can simply write it like this. X is equal to, I'm just going to say 0 plus, not 2 pi times n, but just pi times n, where, again, n is an integer. And that's just a slightly simpler way to represent all of the solutions here because it follows this pattern. Now, this particular example would not follow that pattern, so we do have to list out our 2 separate unit circle solutions plus 2 pi n, where n is an integer, okay? If you have any questions about extending the domain of a trig equation or extending our solutions and representing infinitely many solutions with this notation, please reach out to me at some point, either by email, phone, or Zoom office hours. Otherwise, that's all I have for you right now, and we will talk to you soon.